Hello, welcome to General Relativity Part 2. In this video, we will look at the effects of a reality with a different geometry, curvature, than our flat geometry that we described in special relativity. But first, I want to be precise about what kind of structures have a different curvature than a flat curvature. If we start with a flat structure, for example, a two-dimensional plane, and for this we can imagine a sheet of paper, then any two-dimensional surface that we cannot get by smoothly bending the sheet of paper has a non-flat curvature, or in other words, a different geometry. For example, even though this two-dimensional surface looks like it's curved in our natural way of speaking, we can get it from bending a flat sheet of paper. And this means this two-dimensional surface is actually a flat surface. It has no curvature. So if we want to move from our flat sheet of paper to a non-flat surface, we must stretch and/or shrink the paper at some of its parts. Notice that I said some of its parts because if we stretch or shrink the whole sheet of paper, that is acceptable. It still keeps being a flat geometry. To get a feeling for a non-flat geometry, we will use a sphere, which cannot be wrapped with a sheet of paper, meaning that if we have a flat sheet of paper of any size or form that you want, we cannot wrap it smoothly over a ball. Now in a sphere, a straight line, and I'll remind you that they are called geodesic in a non-flat geometry, is a line that if continued around the whole of the sphere, divides it into two equal halves. Here we have our sphere, our two-dimensional surface, and this is a geodesic of this sphere, because if we split the sphere along this line, we will get exactly the two halves of the sphere. Loosely speaking, in the sphere geometry, parallel means two geodesics that are connected with a third geodesic that is perpendicular to both of them. Here again we have our sphere, our two-dimensional surface, and here we have two geodesics, these two red lines. They are connected by a third geodesic, this blue line, that is perpendicular to both of them. It's perpendicular at this point over here to this geodesic, and it is perpendicular at this point over here to this geodesic. So these two geodesics are parallel to each other at these points. Again, I want to go over what a geodesic in the sphere is. So if we look at 2 points, the geodesic between them in a sphere is part of the line that if we depict around the whole of the sphere, separates the sphere into two exact halves. So this is a geodesic between these 2 points, and the black line over here is also a geodesic between these 2 points going all the way around the sphere. Now with these facts of our sphere geometry, we can notice that two straight lines, two geodesics that start parallel to each other, get closer and meet at a point. Here we have two geodesics, these two red lines, that are parallel to each other at these points over here. They are connected by a third geodesic that is perpendicular to both of them. So these two geodesics start parallel to each other at these points. And as we can see, if we look along the surface of the sphere, they get closer and closer to each other. And at this point over here, they actually meet. Now, in flat geometry, if we have two straight lines, the two red lines that start parallel to each other, they will never get closer to each other, and accordingly, they will never meet at a point. Here we have the exact same situation, but we change the flat geometry to a sphere geometry, and we get that the geodesics, the straight lines, get closer to each other and meet at a point. We start with the exact same scenario of two parallel lines that start parallel to each other, and just by changing the geometry, we change the behavior of these straight lines. One thing to note about this example is that in reality, each point has its own curvature. That is not necessarily, and indeed in most cases is not, the same as the curvature of other points. And this is in contrast to the example of a sphere. So if we look to our sphere, and we use our description of small patches that are stitched one to the other, and together they create this sphere. And we said each triangle has the correct information that we called curvature. So it has a few numbers that tell it how to connect to the triangles around it. Now in a sphere, each triangle will have the same numbers. It will have the same instructions for how to connect to the triangles around it. But in reality, this is not the case. For reality, the case is more like this two-dimensional surface of a rabbit, where, again, if we use the description of building this two-dimensional surface from these flat triangles that are stitched together, then each triangle will have different curvature numbers, because to create this two-dimensional surface of a rabbit, each triangle has to have different instructions for how to stitch to the triangles around it. This triangle has certain instructions, and this triangle over here will have different instructions. This is a better description of what happens in reality. Gravity creates a curvature in reality that is not constant. Okay, let's have a small summary. We said gravity is a curvature in reality. The natural trajectory of a world line is a geodesic. And by combining these two statements, we get that world lines follow the trajectory of geodesics in a geometry created by gravity. Now, this geometry is a geometry where straight lines behave different to the flat geometry straight lines. And this mechanism is the one that explains the effects of gravity. Gravity is just world lines behaving naturally following geodesics in a curved geometry. Now, in this mechanism that explains the known effects of gravity, we can find also some hidden consequences. So, because the procedures that we use to calibrate ongoing change involve straight lines, the calibration is affected by gravity. Gravity affects how straight lines behave, and therefore it affects our calibration mechanism. And this is manifested in the following way. A clock closer to a gravitational source runs slower than a clock that is further away from this source. So the way the source changes the behavior of straight lines close to it is different to how it changes the behavior far away from it. And because this change of behavior is not uniform, we get this effect. Another thing to notice is that in all our discussion, we talked about smooth surfaces or structures. In such structures, a small enough region will be close to flat. And we know how a flat structure behaves. It behaves according to the rules of special relativity. However, black holes and the Big Bang are sharp points in reality. They are not smooth. This means that in a region that includes a black hole or the Big Bang, no matter how small of a region we look at, it will not be close to being flat. As an example, we can look at this two-dimensional surface of a cone, and it has a sharp point. Now, if we look at a patch of this surface that includes this sharp point, this patch can never be close to a flat surface. And no matter how we orient this flat surface, or if we look at a very small patch, no matter how small of a patch we look at, it will never be close to being a flat plane. And this is in contrast to any other patch that does not include this sharp point. And because we only know the complete behavior of flat structures in the theory of special relativity, in these regions we do not know how things behave. We do not have the knowledge of the behavior at a sharp point. Indeed, our theories that rely on the smoothness of structures break down mathematically at these points, meaning we get infinity when we approach this point and we do not know how it behaves. Okay, so let's summarize our understanding of gravity. Gravity is a curvature field. It is created by the mass charge along the information tracks that go through the point holding the charge. The desire of mass is to keep the trajectory of a world line straight along a geodesic, which is the straight line of curved geometries. Curvature affects the behavior of straight lines, and this explains the observed behavior of things that are not affected by forces. Forces are the desire to change the trajectory of a world line from a straight line. So gravity is not a force. It does not want to change the trajectory from a straight line. Gravity operates in a different way. It affects the behavior of these straight lines by creating a curved geometry. Now, because information tracks are straight lines, they exist along geodesics, which means that the mechanism of gravity has a bearing on information. This results in a few things, among them that gravity has extra contributions except for the mass charge, and that clocks run slower closer to a gravitation source. Now, reality is a solution that complies with all of the above. And if we want to look at the whole picture, it has to comply with the effects of the electric charge and the electric field also. Again, as we mentioned, the solution itself is extremely complicated, meaning it's extremely hard to figure out the configuration that will meet all the rules at the same time. But nonetheless, there is a solution that can do this, and reality is just that. So although it's very hard to figure out the complete configuration, especially from our perspective within this configuration, within reality, this configuration is a result of the rules that we covered in this video series. And although there are many interesting phenomena that we did not cover, with this we end our video series. I hope you enjoyed this incredible journey and that we achieved our goal of understanding what Einstein's theory of relativity is all about.